In the 17th century, astronomers were locked in a massive intellectual standoff. Looking up at the sky, they had to decide whether the Earth sat at the dead center of the universe or if it was just another planet orbiting the sun. Look at the intersecting lines on this 17th century Copernican map. Based on the data available at the time, the math for both the Earth-centric and sun-centric models actually worked. You could use either system to accurately predict the movement of the stars. This creates a serious problem. When two completely different mathematical models predict the exact same outcome, how do scientists logically choose which one to believe? If you ask most people today, they'll give you a popular, intuitive rule of thumb. The simplest explanation is usually the correct one. But the universe is incredibly chaotic, and there is no natural law demanding it be easy for human brains to digest. Simplicity on its own does not guarantee truth. The intellectual tiebreaker scientists use is a principle called Occam's razor, or the law of parsimony. It doesn't magically declare which theory is absolutely true. Instead, it provides a strictly logical framework for navigating between equally powerful competing hypotheses. The core logic of the razor actually predates its name. Ancient philosophers like Aristotle sought absolute efficiency when trying to explain nature, arguing that a good demonstration derives from fewer postulates. But the deductive logic we use today was championed by a 14th century English friar and theologian named William of Occam. His preferred version of this principle translates directly to, entities must not be multiplied beyond necessity. In practice, multiplying entities means taking an explanation that already works and weighing it down with extra variables, steps, or assumptions that don't actually improve the prediction. Occam didn't just value simplicity for aesthetic reasons. He weaponized it as a logical tool to aggressively cut away bloated, untestable theories. To understand exactly why these extra entities are so dangerous, we have to look past medieval philosophy and step into modern probability theory. Imagine a man breaks a vase. When confronted, he claims he didn't do it. He says invisible leprechauns pushed it off the table. When you show him security footage proving he knocked it over, he claims the footage was doctored by those same leprechauns. This is called an ad hoc hypothesis, a custom-built excuse invented on the spot to prevent a theory from being disproved. Every time you add a new assumption to your explanation, you introduce a new statistical liability. Even if each individual excuse seems plausible, multiplying them together exponentially shrinks the overall probability of the theory being true. The 20th century philosopher Karl Popper connected this vulnerability to the concept of falsifiability. He argued that theories with fewer assumptions are mathematically preferred simply because their empirical content is greater, making them easier to rigorously test. Occam's razor operates as a mathematical filter. We don't favor hypotheses with fewer parts because they are easier for our brains to understand, but because they carry the least amount of mathematical vulnerability. Today, this medieval heuristic functions as a frontline filter in some of our most high-stakes, data-driven fields. In medicine, diagnostic doctors are taught a variation called the zebra rule. When presented with standard symptoms, you assume a commonplace illness, like a horse, before testing for highly exotic diseases, or zebras. Computer scientists actively apply the razor to deep neural networks to prevent a phenomenon known as overfitting. This chart shows a smooth trend curve compared to a jagged, hyper-complex line. An AI model that creates the jagged line is overwhelmed by statistical noise, memorizing every single data point but missing the broader trend. Training networks to prefer simpler mathematical functions results in vastly more accurate predictions. Whether diagnosing a human body or training a machine mind, the razor protects investigators from getting paralyzed by statistical noise and irrelevant data. But we have to remember one vital caveat. Occam's razor is just a heuristic. It is a rule of thumb, not an unbreakable law of physics. Throughout history, philosophers like Immanuel Kant have proposed an anti-razor, warning that the variety of beings should not rashly be diminished, and entities must not be reduced to the point of inadequacy. Reality frequently defies simple explanations. In quantum mechanics, for instance, we discovered that light behaves as both a continuous wave and a discrete particle at the exact same time. Albert Einstein placed the ultimate constraint on this tool when he stated, "Everything should be kept as simple as possible, but not simpler." Occam's razor does not dictate the absolute truth of the universe. Instead, it serves as our most reliable intellectual compass, pointing us to the most rational, testable starting line when we find ourselves drowning in an endless sea of possibilities.